Imagine a darkness so complete that the very concept of light has been forgotten by the universe itself. A silence so profound that nothing remains to hear it. A cold so absolute that the last whisper of warmth became a memory, trillions upon trillions of years ago. This is not a nightmare. This is not a fantasy. This is the future. The inevitable, patient, gentle future of everything that exists. Welcome, dear friend, to another journey into the cosmic night. I am so glad you are here with me, resting beneath the stars, as we explore together the most profound and peaceful truth the universe has ever whispered. Tonight, we will travel forward in time, far beyond anything a human mind was ever designed to comprehend. We will watch as the last stars flicker and fade, as the darkness slowly embraces all that once burned bright, and as the universe, finally, beautifully, falls asleep. If you find comfort in these words, if this journey brings you peace, please consider subscribing to our channel and leaving a thought in the comments below. Your presence here means more than you know. And now, let us begin. Right now, at this very moment, as you listen to these words, the universe is alive with light. Hundreds of billions of galaxies, each containing hundreds of billions of stars, are burning in the cosmic dark. They have been burning for nearly 14 billion years, and to our brief human eyes, they seem eternal. Look up at the night sky, and you will see them. Those tiny points of light that have guided sailors across oceans, inspired poets to write verses of love and longing, and made children wonder what exists beyond the blue dome of our atmosphere. Each star you see is a furnace of nuclear fire. Deep within their cores, hydrogen atoms are being crushed together with such tremendous force that they fuse into helium, releasing energy in the process. This energy fights against the crushing weight of gravity and creates a delicate balance, a cosmic dance that can last for billions of years. Our own sun, that warm golden orb that rises each morning, has been performing this dance for approximately 4.6 billion years. It has about 5 billion years of hydrogen fuel remaining in its core. 5 billion years. An incomprehensible span of time by human standards. Yet, in the grand story of the universe, this is merely a brief chapter. You see, the stars are not eternal. They never were. They are simply very, very patient. They burn through their fuel slowly, methodically, but inevitably. And when that fuel runs out, they will die. Some stars die in spectacular explosions called supernovae, briefly outshining entire galaxies before fading into darkness. Others, like our sun, will swell into red giants, shedding their outer layers into space before collapsing into dense white dwarfs, cooling slowly over countless eons. But here is the truth that lies at the heart of our story tonight. The universe is not making new stars fast enough to replace the ones that are dying. The great stellar nurseries, those magnificent clouds of gas and dust where new stars are born, are slowly being depleted. The raw material for star formation is running out. This is happening right now. In the Milky Way galaxy, our home among the stars, the rate of star formation has declined significantly over the past several billion years. We are living in what astronomers call the Stelliferous Era, the age of stars. But this age, like all ages, will come to an end. Let us pause here for a moment and simply breathe. Feel the weight of your body. Wherever you are resting, feel the gentle rhythm of your breath. In and out, in and out. The universe breathes too. In its own vast and patient way, it expands, slowly, constantly, carrying the galaxies apart from one another, like leaves scattered by an autumn wind. This expansion, discovered nearly a century ago, means that the universe is growing larger and colder with each passing moment. The energy that exists is being spread thinner and thinner across an ever-increasing volume of space. And this brings us to one of the most fundamental concepts in all of physics. A concept that governs everything from the cooling of your evening tea to the ultimate fate of the cosmos itself. Entropy. Entropy is often described as a measure of disorder, but this definition, while useful, does not capture its full profundity. Entropy is better understood as a measure of how energy is distributed, how spread out it has become. Imagine a cup of hot coffee placed on a table in a cool room. The heat from the coffee, concentrated energy, will flow into the surrounding air. The coffee will cool, and the room will warm slightly until both reach the same temperature. This process is irreversible. The heat will never spontaneously flow back from the room into the coffee, making the coffee hot again while the room becomes cooler. This is forbidden by the second law of thermodynamics, one of the most fundamental laws in all of nature. The second law states that in any closed system, entropy will always increase over time, or at best remain constant. It will never decrease. Energy will always flow from concentrated states to diffuse states, from hot to cold, from ordered to disordered. And the universe itself is a closed system, the largest closed system there is. This means that the entropy of the universe is constantly increasing. The energy that was concentrated in the Big Bang, that primordial explosion of creation, has been spreading out ever since, becoming more diffuse, more evenly distributed with each passing moment. The stars themselves are engines of entropy. They take concentrated nuclear fuel and convert it into light and heat, which radiates outward into the void, spreading energy across the cosmos, increasing the total entropy of the universe. Every time you light a candle, every time a star is born, every time a heart beats with life, entropy increases. This is not a flaw in the design of reality. It is the design. The arrow of time points in the direction of increasing entropy, and there is no way to reverse it. Now, let us turn our gaze forward into the deep future. As the eons pass, as billions of years become trillions, the rate of star formation will continue to decline. The great clouds of hydrogen gas, the raw material from which stars are born, will be consumed, scattered, lost to the expanding void. In approximately 100 trillion years, the last star will be born. It will be a small star, a red dwarf, burning its meager fuel with incredible efficiency. These tiny stars, some no larger than the planet Jupiter, can burn for trillions of years. They are the marathon runners of the stellar world, conserving their energy, stretching their lifespans far beyond those of their larger and brighter cousins. But even the most efficient red dwarf must eventually exhaust its fuel. And when the last of them finally flickers out, the Stelliferous Era will end. The age of stars will give way to something new, the degenerate era. Do not be troubled by this name. In physics, the word degenerate has a specific meaning. It refers to matter that has been compressed to extreme densities, matter in which the normal rules of chemistry no longer apply. In the degenerate era, the only stellar remnants that will remain are white dwarfs, neutron stars, and black holes. These are the corpses of stars. The compressed remains of nuclear furnaces that have long since gone cold. White dwarfs are the cores of stars like our Sun, left behind after the outer layers have been shed into space. They are incredibly dense. A teaspoon of white dwarf material would weigh as much as an elephant on Earth. They no longer generate energy through nuclear fusion. They simply cool, radiating away their residual heat into the darkness, growing dimmer and dimmer over countless eons. Neutron stars are even more extreme. They are the remnants of massive stars that exploded as supernovae. Their cores were compressed so violently that protons and electrons were crushed together to form neutrons. A neutron star is so dense that a teaspoon of its material would weigh billions of tons. These strange objects spin rapidly, some completing hundreds of rotations per second, sending beams of radiation sweeping across the cosmos like cosmic lighthouses. And then there are the black holes. Black holes are perhaps the strangest objects in the universe. They are regions of space where gravity has become so intense that nothing can escape. Not matter, not light, not even time itself as we understand it. When a very massive star dies, its core may collapse so completely that it forms a singularity, a point of infinite density, surrounded by an event horizon, a boundary beyond which nothing can return. Black holes come in many sizes. Stellar black holes, formed from the deaths of massive stars, contain masses ranging from a few times that of our Sun to perhaps 50 or 100 solar masses. Supermassive black holes, lurking at the centers of galaxies, contain millions or even billions of solar masses. Our own Milky Way harbors such a monster at its heart. A black hole called Sagittarius, a star, containing approximately 4 million times the mass of our Sun. In the degenerate era, these black holes will become increasingly important. As the last stars fade, the black holes will remain, patient, silent, waiting in the darkness. But we are getting ahead of ourselves. Let us return to the present and trace the path that leads from now to then. Right now, at this very moment, the universe is approximately 13.8 billion years old. This seems like an unfathomably long time, but in truth, the universe is still in its infancy. We are living in a cosmic morning, the early dawn of an unimaginably long day. If we were to compress the entire future history of the universe into a single year, with today being January 1st, the last star would not burn out until late December, but the universe would continue for countless more years after that, growing darker and colder with each passing moment. Let us walk together, step by step, into this distant future. In approximately 5 billion years, our Sun will exhaust the hydrogen fuel in its core. The core will contract, and the outer layers will expand, transforming our star into a red giant. Its surface will extend outward, perhaps swallowing Mercury, Venus, and possibly even the Earth. The inner planets will be vaporized, returned to the cosmic dust from which they formed. Any remnants of human civilization, any monuments, any memories carved into stone will be erased forever. But do not weep for this loss. By that time, 5 billion years hence, humanity will have either perished or evolved into something beyond our current understanding, or spread to other star systems, carrying the light of consciousness across the galaxy. After its red giant phase, our sun will shed its outer layers, creating a beautiful planetary nebula, a glowing shell of gas expanding outward into space. At its center, the exposed core of the sun will remain, a white dwarf. Containing about half the original mass of the star, compressed into a sphere roughly the size of the Earth. This white dwarf, which we might call Sol, will glow with a faint bluish-white light, slowly cooling over the eons, fading from visibility, becoming dimmer and dimmer as entropy takes its toll. Let us pause again and simply be present. The future we are describing is so distant, so removed from human experience, that it can feel abstract, unreal, like a story told about someone else's dream. But this is your universe. This is the cosmos that gave you birth. The atoms in your body were forged in the hearts of ancient stars. You are made of stardust. And one day, in the far, far future, that stardust will return to the void from which it came. This is not a tragedy. This is simply the nature of existence. Everything that begins must end. Everything that burns must cool. Everything that lives must die. And yet, in this moment, right now, you are alive, you are conscious, you are aware of yourself and of the universe around you. This is a miracle that no amount of entropy can diminish. So breathe, rest. Know that you are part of something vast and ancient and beautiful, and let us continue our journey together. In the comments below, I invite you to share what you are feeling. Does this vision of the future bring you peace, or does it stir something else within you? There is no right or wrong answer, only your truth. As we continue our journey into the future, let us expand our perspective, from our single dying sun to the galaxy that contains it. The Milky Way, our cosmic home, is a spiral galaxy containing between 200 billion and 400 billion stars. It spans approximately 100,000 light-years from edge to edge and rotates slowly, completing one revolution every 230 million years. When you look up at the night sky on a clear evening and see that faint band of light stretching across the heavens, you are looking at the disk of our galaxy Edge-On. You are seeing the combined glow of billions of distant stars, too far away to resolve individually, blending together into a river of light. The ancient Greeks called this river Galaxias Kyklos, the Milky Circle, from which we derive our modern name. They did not know that those countless points of light were suns like our own. They did not know that our sun was merely one star among hundreds of billions, adrift in a vast cosmic ocean. But now we know, and with this knowledge, we can trace the future of our galaxy, just as we traced the future of our sun. In approximately 4.5 billion years, something remarkable will happen. The Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor, located approximately 2.5 million light-years away. Right now, at this very moment, Andromeda is approaching us at a speed of approximately 110 kilometers per second. This may sound fast, but at such vast distances, it will take billions of years for the two galaxies to meet. When they do, the collision will not be the violent catastrophe that the word collision might suggest. Galaxies are mostly empty space. The distances between stars are so enormous that when two galaxies merge, the stars pass by one another like ships in the night. Individual stellar collisions will be extremely rare. What will change is the structure of both galaxies. The beautiful spiral arms of the Milky Way will be distorted, stretched, torn apart by gravitational forces. Stars will be flung outward into intergalactic space. Others will fall inward, toward the merged galactic center. Over the course of several billion years, the two galaxies will dance around each other, separating and reuniting multiple times until finally settling into a single large elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda. At the center of Milkomeda, the two supermassive black holes from the original galaxies will slowly spiral toward each other. Eventually, they will merge, creating a single supermassive black hole of tremendous mass. This merger will release gravitational waves, ripples in the fabric of space-time itself, that will propagate outward across the universe at the speed of light. But this merger, as dramatic as it sounds, is merely a prelude to what follows. The formation of Milkomeda will not halt the decline of star formation. It will not reverse the increasing entropy of the cosmos. It will simply create a larger stage on which the final acts of the stellar drama will be performed. Let us now leap forward, far beyond the merger of galaxies, into an era when the very concept of a galaxy will begin to lose its meaning. As the universe continues to expand, driven by the mysterious force we call dark energy, the distances between galaxy groups will increase. Galaxies that are gravitationally bound to one another, like the Milky Way and Andromeda, will remain together. But galaxies beyond our local group will recede ever faster into the distance. Eventually, they will cross our cosmic horizon. They will be carried away so quickly that the light they emit will never be able to reach us. They will vanish from our observable universe, not because they have ceased to exist, but because the expanding space between us has made them forever unreachable. In the far future, the night sky of Milkomeda will contain no other galaxies. The countless spiral and elliptical forms that we can photograph today, the deep field images showing thousands of galaxies in every direction, will be replaced by emptiness. Only the stars of our own merged galaxy will remain visible, and even those stars will be fading. As the trillions of years pass, the fuel for star formation will continue to be depleted. New stars will become increasingly rare. The brilliant blue giants, which burn through their fuel in mere millions of years, will be the first to disappear. They will explode as supernovae, or collapse directly into black holes. And no new blue giants will be born to replace them. The yellow stars, like our sun, will follow. Each generation will be smaller, dimmer, longer lived than the last, as the available hydrogen becomes increasingly scarce. Finally, only the red dwarfs will remain. These tiny stars, some containing less than 1/10 the mass of our Sun, are incredibly efficient with their fuel. A red dwarf born today might continue to shine for 10 trillion years or more than 700 times the current age of the universe. In the far future, these patient little stars will be the last sources of light. They will burn with a dim red glow, barely visible even from nearby, casting just enough warmth to keep any surviving planets from freezing completely. Around these red dwarfs, life might still be possible. Planets orbiting close to their dim parent stars, bathed in perpetual red twilight, might harbor oceans of liquid water beneath thick atmospheres. On such worlds, strange and wonderful creatures might evolve, looking up at their solitary sun, never knowing that the universe was once filled with light. But even the red dwarfs cannot burn forever. In approximately 100 trillion years, give or take a few trillion, the last red dwarf will exhaust its hydrogen fuel. Its core will contract, and it will become a white dwarf, a cooling ember in the cosmic darkness. And with its passing, the Stelliferous Era will end. The age of stars, which began when the first generation of stars ignited a few 100 million years after the Big Bang, will finally come to a close. For 100 trillion years, the universe was illuminated by nuclear fire, by starlight that warmed planets and powered the chemistry of life, by the radiance of countless suns burning in the void, and then darkness. Take a moment to absorb this. Let it wash over you like a gentle wave. The universe will not end when the last star dies. It will continue for an almost inconceivable span of time, but it will continue in darkness, a darkness unbroken by any natural light. This transition from light to darkness is not sudden, it is gradual, patient, like falling asleep after a long day. The universe does not rage against the dying of the light. It simply lets go. And in that letting go, there is a strange kind of peace, the frantic energy of stellar formation, the violence of supernovae, the fierce gravitational struggles of merging galaxies. All of this will be over. The universe will enter a period of calm, of stillness, of quiet contemplation. In the degenerate era that follows, the remaining objects will be white dwarfs, neutron stars, and black holes. These stellar corpses will drift through the darkness, cooling slowly, interacting rarely, waiting for processes that operate on timescales beyond human comprehension. Let us speak more about these remnants, these survivors of the stellar age, the white dwarfs, numbering in the hundreds of billions within our galaxy alone, will continue to radiate their residual heat into space. They will grow cooler and dimmer with each passing eon. Their surfaces, once white-hot, will gradually shift through yellow to orange, to red, and finally to infrared, visible only to instruments that can detect heat radiation. After approximately 1 quadrillion years, one followed by 15 zeros, even the infrared radiation will become too faint to detect. The white dwarfs will have cooled to the temperature of the cosmic background. They will be in thermal equilibrium with the universe itself, neither absorbing nor emitting any net energy. At this point, they will have become something new, something that does not yet exist anywhere in the universe, because the universe is not yet old enough for any white dwarf to have cooled this far. They will become black dwarfs. We will speak much more about black dwarfs later in our journey. For now, simply know that they represent the final fate of stars like our Sun: cold, dark, crystalline spheres, drifting forever through the void. The neutron stars will undergo a similar fate. Though far denser and hotter than white dwarfs, they too will eventually radiate away their thermal energy. They will cool and solidify and become dark remnants, distinguishable from black dwarfs only by their extreme density and the exotic matter of which they are composed. And then there are the black holes, the strangest objects of all. In many ways, the true protagonists of our story. Black holes do not cool like other objects. They do not radiate heat in the conventional sense. Their event horizons swallow everything that crosses them, including any thermal radiation that might allow them to equilibrate with their surroundings. And yet, black holes are not eternal. This is one of the most remarkable discoveries of 20th century physics, made by the brilliant theoretical physicist Stephen Hawking in 1974. Hawking showed that black holes emit a faint radiation, now called Hawking radiation in his honor. This radiation arises from quantum mechanical effects near the event horizon, and it causes black holes to slowly lose mass over time. The process is extraordinarily slow. A stellar black hole containing 10 times the mass of our Sun would take approximately 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros, a number so large that it defies any attempt at comprehension. A supermassive black hole, like the one at the center of our galaxy, would take even longer, perhaps 10 to the power of 100 years, a googol of years before it finally evaporated away. But in a universe of infinite patience, even these enormous timescales will pass. And when they do, the black holes too will be gone, leaving behind only a faint wash of radiation, spreading outward into the expanding void. This brings us to the era that gives our documentary its name, the Black Hole Era, a period of cosmic history that will last far longer than all the preceding eras combined, and during which black holes will be the dominant objects in the universe. But before we enter the Black Hole Era, there are other processes we must discuss, other events that will shape the universe during the long transition from the stellar age to the age of darkness. And so, let us continue. As we journey deeper into the future, we must turn our attention to matter itself, the atoms and particles that make up everything we see, everything we touch, everything we are. In our daily experience, matter seems permanent. A rock will remain a rock. A diamond will remain a diamond. The iron at the center of the Earth has been there for 4.5 billion years and shows no sign of changing. But physics teaches us that this permanence is an illusion. On sufficiently long timescales, even the most stable matter will decay, will transform, will eventually cease to exist in its current form. This is not mere speculation. It is a prediction that emerges from our deepest theories of particle physics. Theories that have been tested and confirmed in countless experiments. let us explore what happens to matter. In the long dark future of the universe, all ordinary matter is made of atoms, and atoms are made of smaller particles, protons and neutrons in the nucleus, electrons orbiting around them. Protons and neutrons are themselves made of even smaller particles called quarks, held together by the strong nuclear force, one of the four fundamental forces of nature. For a long time, physicists believed that protons were absolutely stable, that a proton would remain a proton forever, never decaying into anything else. But our modern theories, particularly the grand unified theories that attempt to describe all the fundamental forces except gravity in a single framework, suggest that protons may not be eternal after all. According to these theories, protons can decay, but with an extraordinarily long half-life. Current experiments have placed a lower limit on the proton's half-life at approximately 10 to the power of 34 years, far longer than the current age of the universe. If protons do decay, the consequences for the far future are profound. Over timescales of 10 to the power of 40 years or longer, all ordinary matter will gradually disintegrate. The protons will decay into lighter particles, positrons and pions, which will themselves decay or annihilate, leaving behind only radiation and the lightest stable particles. This means that the white dwarfs, the neutron stars, the black dwarfs we mentioned earlier, all of these objects are temporary. On sufficiently long timescales, they will evaporate, not through Hawking radiation like black holes, but through the slow decay of the protons that compose them. Imagine a black dwarf, a cooling remnant of a sun-like star, drifting through the darkness of the far future, over trillions upon trillions of years. It will slowly lose mass as the protons in its iron core, one by one, decay into radiation. The process is unimaginably slow, so slow that nothing in our experience provides an adequate comparison. But it is relentless, inevitable, and when it is complete, the black dwarf will be gone, replaced by a faint cloud of radiation dispersing into the void. But wait, we spoke of neutron stars, and neutron stars are made primarily of neutrons, not protons. Does this mean they are immune to proton decay? Not quite. Free neutrons, neutrons that are not bound within an atomic nucleus, are actually unstable. They decay into protons, electrons, and antineutrinos, with a half-life of only about 10 minutes. But neutrons within a neutron star are not free. They are held in place by enormous gravitational and nuclear forces. In this environment, they behave differently. Some of them may convert back into protons, which can then decay. Others may participate in exotic processes that we do not yet fully understand. The precise fate of neutron stars in the far future remains an active area of research, but the general conclusion is clear. They too will eventually decay, eventually dissolve, eventually return their matter to the void. And what of the electrons? Those tiny particles that orbit atomic nuclei, that flow through wires as electric current, that are essential to the chemistry of life. Electrons are among the lightest particles with electric charge. As far as we know, they are absolutely stable. There is no lighter charged particle for them to decay into, but even electrons will not survive the far future unchanged. In the presence of positrons, the antimatter counterparts of electrons, they will annihilate, converting their combined mass into gamma-ray photons. As protons decay, they produce positrons. These positrons will eventually find electrons and annihilate with them. Over vast spans of time, the electrons and positrons will find each other and vanish in flashes of light. Eventually, ordinary matter as we know it will cease to exist. The universe will contain only black holes, photons, neutrinos, and perhaps some exotic particles that we have not yet discovered. Let us pause and consider what this means. Everything you have ever known, every person, every place, every object, is made of matter that will not last forever. The very atoms of your body will one day decay into radiation. This might sound frightening, but remember how far in the future this lies. The timescales we are discussing are so vast that they make the current age of the universe seem like the blink of an eye. And consider this: long before proton decay becomes significant, long before matter begins to dissolve, the universe will have been dark for countless eons. Life as we know it will have ended, not because of the decay of matter, but simply because there will be no energy sources left to sustain it. The decay of matter is not a catastrophe. It is simply the final chapter in a very, very long story. A story that will already be complete by the time that chapter begins. There is a certain beauty in this, a certain completeness. The universe began with energy, with light, with the primordial fire of the Big Bang. Over billions of years, this energy condensed into matter, formed stars and planets and galaxies, gave rise to life and consciousness. And in the end, matter will return to energy, will dissolve back into radiation, completing a cosmic cycle that spans an almost unimaginable span of time, from light to matter, and back to light again. This is not destruction. This is transformation. The universe does not waste anything. It simply changes, evolves, becomes something new. And in this transformation, there is no loss, only change, only the endless dance of energy taking different forms. Now, as we continue our journey, let us turn our attention fully to the black holes, those strange and wonderful objects that will dominate the universe for most of its future existence. The black hole era proper begins when black holes become the most significant gravitationally bound objects in the universe. This occurs sometime after the last stars have faded, after the white dwarfs and neutron stars have cooled to invisibility, after matter has begun its slow decay. During this era, which will last from approximately 10 to the power of 40 years, to 10 to the power of 100 years or beyond, black holes will reign supreme. They will be the only objects massive enough to significantly curve space-time, the only objects capable of dramatically affecting their surroundings. And yet, even as they reign, they will be slowly dying, evaporating through Hawking radiation, particle by particle, quantum fluctuation by quantum fluctuation. Let us explore this process in more detail. In 1974, a young British physicist named Stephen Hawking made a discovery that would revolutionize our understanding of black holes and provide one of the most important clues to the ultimate fate of the universe. Hawking was attempting to combine two of the greatest theories in physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales. These two theories are notoriously difficult to reconcile. General relativity treats space-time as smooth and continuous, while quantum mechanics reveals a world of discrete particles and fundamental uncertainty. Finding a complete theory that unifies them, a theory of quantum gravity, remains one of the greatest unsolved problems in physics. But Hawking found that even without a complete theory of quantum gravity, he could say something profound about what happens at the boundary of a black hole, at the event horizon, where the two realms meet. To understand Hawking's discovery, we must first understand something about the quantum vacuum. In classical physics, the vacuum is simply empty space. Nothing exists there. Nothing happens. But in quantum mechanics, the vacuum is far from empty. It seethes with activity, with virtual particles that pop into existence and vanish again, in pairs, on timescales so short that they do not violate the conservation of energy. These virtual particles come in matter-antimatter pairs, an electron and a positron, a quark and an antiquark. They appear, interact briefly, and then annihilate each other, returning their borrowed energy to the vacuum. Under normal circumstances, these virtual particles have no lasting effect. They are ghosts, appearing and disappearing too quickly to be directly observed. But near the event horizon of a black hole, something remarkable can happen. If a pair of virtual particles appears very close to the event horizon, it is possible for one particle to fall into the black hole, while the other escapes into space. The escaping particle becomes real, carrying energy away from the black hole, while the infalling particle effectively carries negative energy, reducing the mass of the black hole. This is Hawking radiation, a slow but steady emission of particles from the vicinity of a black hole, causing the black hole to lose mass over time. The rate of Hawking radiation depends on the mass of the black hole, in a surprising and counterintuitive way. Smaller black holes radiate faster than larger ones. This can be understood by thinking about the surface gravity of the black hole. The strength of gravity at its event horizon. Smaller black holes have higher surface gravity, which creates more intense quantum effects, and thus more rapid emission of Hawking radiation. For a stellar black hole with a mass of 10 suns, the Hawking radiation is incredibly faint. The black hole would emit energy at a rate of approximately 10 to the power of negative 29 watts, far less than the cosmic microwave background radiation that fills the universe. At such a low emission rate, the black hole would take approximately 10 to the power of 67 years to evaporate, a timescale so vast that it dwarfs even the ages we have been discussing. For a supermassive black hole, with a mass of billions of suns, the timescale is even longer, perhaps 10 to the power of 100 years, a googol of years. But here is the key insight. As a black hole loses mass, it gets smaller. And as it gets smaller, it radiates faster. The process accelerates. In the final moments of a black hole's life, this acceleration becomes dramatic. The last 10,000 tons of the black hole will evaporate in roughly 1 second, releasing approximately 10 to the power of 23 joules of energy, equivalent to 1,000,000,000 1-megaton nuclear explosions. This final burst of Hawking radiation is the death cry of the black hole, a flash of light in the darkness, announcing that another of the universe's great gravitational engines has ceased to exist. And then, silence. The black hole is gone, replaced by a fading shell of radiation, expanding outward into the void. Let us sit with this image for a moment. A black hole that has existed for countless eons, that has swallowed stars and gas and perhaps entire galaxies, that has warped space-time so severely that light itself could not escape. Slowly, patiently evaporating, particle by particle, quantum fluctuation by quantum fluctuation, growing smaller, growing hotter, radiating more and more intensely, until finally, in one brilliant flash, it is gone. This is how the black holes will die, one by one, over timescales beyond imagination, each ending in a burst of light, a final flare of energy before fading into the darkness. The Hawking radiation from black holes is one of the most profound predictions in all of physics. It connects gravity, quantum mechanics, and thermodynamics in a single elegant framework. It tells us that black holes are not truly black. They glow, however faintly. They have a temperature, however small. They are subject to the second law of thermodynamics. However slowly they may approach equilibrium. And most importantly for our story, it tells us that black holes are not eternal. They will eventually evaporate. And when the last black hole has vanished, the universe will enter its final era. But we are getting ahead of ourselves. The black hole era is long, unimaginably long. And during this time, strange and wonderful things will happen. Let us continue to explore. Imagine the universe during the black hole era. The stars have been dark for trillions upon trillions of years. The white dwarfs and neutron stars have cooled to invisibility. Ordinary matter is slowly decaying, particle by particle, returning to the radiation from which it came. And through this darkness, the black holes drift, silent, patient, eternal, or so they seem. During this era, black holes are the most important objects in the universe. They are the only remaining concentrations of mass, the only objects that significantly curve spacetime, the only sources of energy, however faint, in an otherwise dead cosmos. Let us examine these lords of the darkness and understand their nature more deeply. Black holes come in many sizes, each with its own character, its own destiny. The smallest black holes that might exist, primordial black holes potentially formed in the early universe, could have masses as small as a mountain. These tiny black holes, if they exist, would have long since evaporated through Hawking radiation. They would have vanished within the first few billion years after the Big Bang. Their brief existence would have been a mere flash in the cosmic story. Stellar black holes, formed from the collapse of massive stars, contain masses ranging from a few times that of our Sun to perhaps 100 solar masses. These are the black holes most commonly discussed in astronomy, and they form the bulk of the black hole population. Intermediate mass black holes, containing hundreds to thousands of solar masses, are more mysterious. We believe they exist, formed perhaps from the mergers of stellar black holes, or from the direct collapse of massive gas clouds, but they have been difficult to observe directly. And then there are the supermassive black holes, the giants containing millions or billions of solar masses, lurking at the centers of galaxies. These are the true monarchs of the black hole era, the objects that will persist the longest, the final bastions of structure in an otherwise structureless universe. During the black hole era, the black holes will not simply sit passively, waiting to evaporate. They will interact with each other and with their environment in various ways. Black holes can merge with each other. When two black holes come close enough, they will spiral toward each other, emitting gravitational waves, ripples in space-time, and eventually collide, forming a single larger black hole. This process was first directly detected in 2015, when the LIGO Observatory measured gravitational waves from two stellar black holes merging approximately 1.3 billion light-years away. It was one of the great triumphs of modern physics, confirming a prediction that Einstein had made a century earlier. In the black hole era, mergers will continue to occur. Black holes will find each other across the vast distances of intergalactic space, drawn together by gravity, spiraling inward over billions of years, and finally combining into ever larger objects. The supermassive black holes at the centers of galaxies will grow through these mergers. As galaxies collide and their central black holes combine, these monsters will become even more massive, approaching and perhaps exceeding 10 billion solar masses. But mergers alone cannot prevent the eventual evaporation of black holes. Each merger creates a larger black hole, which takes longer to evaporate. But no merger adds mass to the total. It only concentrates existing mass into fewer objects. And the total mass of black holes in the universe is finite. Eventually, there will be no more mergers to occur. The black holes will have grown as large as they can, and they will begin their long, slow, irreversible decline. Let us consider the experience of a black hole, if such a thing can be said to have experience, during this long era, from the perspective of an outside observer. The black hole exists in a state of profound stillness. It does not burn like a star. It does not spin down like a neutron star. It simply is. Occasionally, something might fall into the black hole, a stray particle wandering through the void, a dark matter halo that has persisted since the early universe, another black hole approaching for a merger. Each such event would add slightly to the mass of the black hole, prolonging its existence by some tiny amount. But these events would become increasingly rare as the eons pass. The universe would become increasingly empty, increasingly sparse, and the black holes would wait, alone, in the darkness. And all the while, Hawking radiation would be carrying away mass, particle by particle, so slowly that no change would be perceptible over any timescale we can imagine, but relentlessly, inevitably. There is something almost meditative about this image, a black hole waiting in darkness, losing itself so slowly that the process is imperceptible, yet knowing, if it could know, that the end is coming. Perhaps this is what peace looks like, on cosmic scales. Not the frantic activity of stellar nurseries, not the violent explosions of supernovae, but this quiet, patient waiting, The universe during the black hole era is not dead. Not exactly. It is simply resting. It has done its work, created its stars, evolved its life, explored its possibilities. And now it is winding down, approaching equilibrium, approaching the final state from which it will never return. I wonder, as you listen to these words, what thoughts pass through your mind? Do you feel small, contemplating these vast expanses of time and space? Or do you feel connected, part of something immense and eternal? Do you feel sad, knowing that all things must end? Or do you feel peaceful, knowing that the ending is gentle, gradual, unhurried? I invite you to share your reflections in the comments. Let us create a space where we can contemplate these cosmic truths together, where we can find meaning in the vastness and comfort in each other's company. We are all travelers on this cosmic journey, and though the destination may be darkness, the journey itself is filled with light. As the black hole era progresses, the universe will become increasingly silent. The events that punctuated earlier eras, the explosions, the collisions, the emissions of light and radiation, will become vanishingly rare. Let us try to comprehend the silence of this era. Let us immerse ourselves in its profound stillness. Imagine floating in space during the black hole era. You are surrounded by darkness, absolute and complete. There are no stars to provide light, no nebulae to glow with reflected radiation. The only visible objects are the black holes themselves, and even they are visible only indirectly through the faint glow of Hawking radiation, or through the distortion they create in any background light that happens to pass nearby. But there is almost no background light. The cosmic microwave background, that faint afterglow of the Big Bang that fills the universe today, has been redshifted and diluted by the expansion of space. It is now so faint, so cold, that it is indistinguishable from absolute zero. The universe has no temperature, no energy, no activity, except for the slow, patient, imperceptible evaporation of the black holes. Time itself seems different in such a universe. When nothing is happening, when no events mark the passage of moments, what does time even mean? This is not just a philosophical question. Physics tells us that time is fundamentally connected to change, to the sequence of events, to the transformation of states. In a universe where nothing changes, where no events occur, time becomes undefined, meaningless. During the black hole era, time still exists in a technical sense. The black holes are still evaporating, however slowly. Hawking radiation is still being emitted, however faintly. But the rate of change is so infinitesimally small that from any practical perspective, the universe has frozen. And yet, even in this frozen universe, interesting things can still happen, given enough time. Quantum mechanics tells us that any process that is not strictly forbidden will eventually occur, given sufficient time, even if the probability of that process is vanishingly small. If you wait long enough, it will happen. This principle has strange implications for the black hole era. Consider a black hole floating in the void. It is surrounded by empty space, the vacuum of quantum mechanics, seething with virtual particles that appear and disappear on timescales too short to observe. Normally, These virtual particles annihilate each other and vanish. But quantum mechanics allows for the possibility, however remote, that a pair of virtual particles will appear far enough apart that they do not annihilate. Instead, they become real particles, spontaneously created from the quantum vacuum. This process is called vacuum fluctuation, and it is extraordinarily rare. But on the timescales of the black hole era, it becomes significant. Over timescales of 10 to the power of 100 years or longer, the quantum vacuum will spontaneously produce all sorts of particles. Electrons, protons, entire atoms might flicker into existence, persist for a while, and then disappear again. In principle, the quantum vacuum could spontaneously produce anything: a star, a planet, a brain that exists for a single moment, thinks a single thought, and then dissolves back into the void. These hypothetical, spontaneous creations are called Boltzmann brains, after the physicist Ludwig Boltzmann, who first considered such possibilities. They are deeply controversial, and many physicists believe that our theories must be wrong in some way if they predict such objects. But setting aside the Boltzmann brains, the point remains. Even in the silence of the black hole era, the quantum vacuum is not truly silent. It whispers. It fluctuates. It creates and destroys on timescales beyond comprehension. Let us consider another strange possibility that might occur during the black hole era. A white dwarf or a black dwarf, floating through the void, might encounter another such object. The probability of such an encounter is incredibly low. Given the vast distances between objects in the expanded universe, but with enough time, even incredibly unlikely events will occur. If two black dwarfs collide, the result depends on their combined mass. If the combined mass exceeds a certain threshold, approximately 1.4 times the mass of our Sun, the merged object will be unstable. It will collapse. And in the darkness of the black hole era, a new light will briefly shine. The collapse of a merged black dwarf would trigger nuclear reactions. The iron and carbon that compose these cold remnants would be compressed to temperatures and densities high enough to fuse. The result would be a thermonuclear explosion, a supernova of sorts, lasting perhaps a few seconds to a few days. For a brief moment, there would be light in the universe, a flare of nuclear fire in the endless dark, a reminder of the stellar age that ended so long ago. And then, darkness again. The explosion would fade, the debris would disperse, and the silence would return. These events, these brief flares of activity in the long silence, would become the only punctuation marks in the story of the black hole era. Rare, unpredictable, separated by spans of time that make geological ages seem instantaneous. And all the while, the black holes would continue to evaporate, slowly, patiently, approaching their eventual demise. Let us rest here for a moment in the silence. Feel the stillness around you. Feel the peace that comes from letting go of activity, of striving, of doing. The universe in the black hole era has let go. It has completed its work, and now it rests. It is not dead. It is simply still, waiting, existing, being. There is a lesson here, perhaps about the value of stillness, about the peace that comes when we stop struggling against the flow of time. We spend so much of our lives in motion, in activity. in the constant pursuit of goals and desires. But the universe shows us that there is another way, a way of patience, of acceptance, of simply being present to what is. Perhaps in our own small way, we can touch that peace, feel it, even for a moment, as we rest here together, listening to the silence of the cosmos. And now, we approach the climax of the black hole era, the moment when the last of these great gravitational engines finally vanishes. We have spoken of timescales that are almost impossible to comprehend. 10 to the power of 67 years for a stellar black hole to evaporate. 10 to the power of 100 years for a supermassive black hole. Let us try once more to grasp the magnitude of these numbers. The current age of the universe is approximately 13.8 billion years. Written in scientific notation, this is about 10 to the power of 10 years. 10 to the power of 67 years is 10 to the power of 57 times longer than the current age of the universe. That is a 1 followed by 57 zeros, a number so large that there is no meaningful comparison to anything in human experience. If the current age of the universe were a single second, 10 to the power of 67 years would be approximately 30 trillion years. Still an incomprehensible number, and yet this is merely the timescale for stellar black holes. The supermassive black holes will take even longer, perhaps 10 to the power of 100 years, a Google of years. These are the timescales on which the black hole era will play out. These are the eons that will pass before the final black hole evaporates. As the black hole era progresses, the smallest black holes will evaporate first. Remember, smaller black holes radiate more intensely than larger ones, and thus disappear more quickly. The stellar black holes, containing a few tens of solar masses, will be among the first to go, one by one, over spans of 10 to the power of 67 years. They will evaporate, each ending in a final flash of Hawking radiation, a burst of light and particles, before fading into nothing. The intermediate mass black holes will follow, containing hundreds or thousands of solar masses, taking slightly longer to evaporate, but following the same inevitable path. And finally, the supermassive black holes, the giants at the centers of former galaxies, will begin their final decline. These monsters, containing billions of solar masses, will persist the longest, but even they cannot evade thermodynamics. Imagine the final supermassive black hole, the last significant concentration of mass in the universe. Perhaps it contains 1 trillion solar masses, accumulated over countless eons through mergers and accretion. Perhaps it is the result of multiple galactic clusters combining their central black holes into a single gravitational behemoth. This black hole would have an event horizon roughly the size of the solar system. Its Hawking radiation would be extraordinarily faint. The temperature of its event horizon would be a tiny fraction of a degree above absolute zero. And yet, it would be evaporating, losing perhaps 1 atom's worth of mass every trillion years, but losing it nonetheless. Over timescales that dwarf anything we have previously discussed, this final black hole would slowly shrink. Its event horizon would contract, its temperature would rise, its rate of radiation would increase. As it shrank, the black hole would pass through various stages. At some point, it would have the mass of a galaxy, then a star, then a planet, then a mountain. With each reduction in mass, the evaporation would accelerate. The temperature of the Hawking radiation would increase. The black hole would begin to glow, first in the infrared, then in visible light, then in ultraviolet, then in X-rays, then in gamma rays. In its final moments, the black hole would be a tiny, incredibly hot, intensely radiating object. It would glow with a brilliance that had not been seen in the universe for eons upon eons, and then, in a final flash, it would be gone. This moment, the evaporation of the last black hole, marks the end of the black hole era and the beginning of something new. The universe would now be truly empty. No stars, no black holes, no white dwarfs, no neutron stars. Nothing but radiation, particles, and the quantum vacuum itself. This is the era that physicists call the Dark Era, or sometimes the Final Era, the era in which nothing significant will ever happen again. But let us not rush too quickly past this moment, the death of the last black hole. Let us linger here and appreciate its significance. For almost all of cosmic history, there have been concentrations of mass in the universe. Stars, galaxies, black holes, objects that curve space-time, that attract other objects, that create structure and complexity. The death of the last black hole ends this, forever. There will never again be a significant concentration of mass. There will never again be an object that bends light or shapes the geometry of space. The universe will be flat, empty, featureless, a void without form, without structure, without change. This is not an end to be mourned. It is simply the final state of a process that has been unfolding since the beginning of time, the process of entropy increasing, of energy spreading out, of the universe approaching equilibrium. The death of the last black hole is the universe, finally, completely letting go. And yet, even after the last black hole has evaporated, the universe will continue to exist. It will not end. It will simply persist in this final equilibrium state forever. What will this existence be like? We will explore this in the passages to come. We have arrived at the end of the cosmic story, the moment when the universe reaches its final state, from which it will never significantly depart. This state is called the heat death, a term that might seem paradoxical. How can death be associated with heat? The answer lies in thermodynamics and in the concept of entropy that we discussed earlier. The heat death does not mean that the universe becomes hot. Quite the opposite. It means that the universe reaches a state of maximum entropy, a state of perfect uniformity, where all energy has been evenly distributed and no further work can be done. Think back to our example of the cup of hot coffee. Left on a table, it will cool until it reaches the same temperature as the room. At that point, no further heat transfer can occur. The system has reached thermal equilibrium. The heat death is the cosmic version of this process. The universe has cooled, expanded, evaporated, until all of its energy is evenly distributed throughout all of space. There are no hot spots and cold spots, no concentrations of energy that could be tapped to do useful work. Just a uniform, featureless, incredibly dilute sea of radiation and particles. What does the universe look like in this final state? It is almost impossible to describe, because our language is built around the assumption that things exist, that events happen, that there is structure and change. In the heat-death universe, none of these assumptions hold. There are no objects. The particles that remain: photons, neutrinos, perhaps some exotic matter we have not yet discovered, are so dilute that interactions between them are vanishingly rare. They drift through the void, never encountering each other, never forming structures, never combining into anything larger than themselves. There are no events. Nothing happens. Nothing changes. The particles continue to drift. The space continues to expand. But from the perspective of any hypothetical observer, everything is static, frozen, eternal. There is no time, in the sense that matters. Time has ceased to exist. When nothing changes, when no events mark the passage of moments, time becomes meaningless. The universe simply is in a perpetual present, without past or future. The temperature of this universe is almost absolute zero, but not quite. The expansion of space has stretched all radiation to incredibly long wavelengths, corresponding to temperatures of tiny fractions of a degree above zero. This is as cold as anything can be. According to quantum mechanics, absolute zero. True zero temperature is impossible to achieve. There will always be some residual energy, some minimal fluctuation. However small, the temperature will never quite reach zero. And so the heat-death universe is not truly dead. It is simply at its minimal state of activity. It has the least possible amount of organization, the most possible amount of disorder. It is as close to nothing as the universe can be while still existing. Let us sit with this image. Let it wash over us. The universe, which began in a blaze of light and energy, which formed galaxies and stars and planets, which gave rise to life and consciousness and love, has become an infinite, uniform, featureless void, colder than cold, emptier than empty, quieter than silence, and it will remain this way forever. You might think this is a sad ending, a tragedy of cosmic proportions, everything we know and love, reduced to nothing. But I want to suggest a different perspective. The heat-death is not an ending. It is a completion. The universe has done everything it could do, explored every possibility, achieved every state, and now it rests in perfect equilibrium, in eternal peace. Think of it as a long, deep, dreamless sleep. The universe has been awake for so long, active for so long, burning with light and churning with change. And now it sleeps, not the troubled sleep of exhaustion, but the peaceful sleep of fulfillment. Everything the universe could be, it has been. Everything it could do, it has done. And now it is at peace. There is comfort in this, if you look for it. The universe does not fight against its fate. It does not rage against the dying of the light. It simply accepts. And in that acceptance, there is a kind of grace, a kind of beauty. Perhaps we too can learn from this. Perhaps we can accept the impermanence of all things, including ourselves, with the same grace, the same peace. We are part of the universe. We share its nature, its destiny. And if the universe can accept the heat-death with equanimity, perhaps so can we. Even in the heat-death state, Even in the eternal silence of the final era, the universe is not truly still. Quantum mechanics tells us that the vacuum of space is never truly empty. It seethes with activity, with virtual particles appearing and disappearing, with fluctuations in the underlying fields that permeate all of existence. These quantum whispers are the last remnants of activity in the heat-death universe. They are incredibly subtle, incredibly faint, but they never quite cease. Let us explore what this means for the far, far future. The quantum vacuum is often described as a sea of potential, a reservoir from which particles can emerge and into which they can return. Under normal circumstances, this process is balanced. Particles appear in pairs and annihilate almost immediately. No net change occurs, but on sufficiently long timescales, the balance can be broken. Random fluctuations can occasionally produce something lasting, a particle that escapes before annihilation, a configuration of fields that persists for a while. In the heat-death universe, these fluctuations are the only events that occur, and they are vanishingly rare, but in an infinite future, even the rarest events will happen, eventually. We mentioned earlier the concept of Boltzmann brains, spontaneous fluctuations that produce organized structures, including possibly conscious observers. This remains one of the most controversial ideas in cosmology. If our theories are correct, then over sufficiently long timescales, the quantum vacuum will spontaneously produce, well, anything. Stars, planets, galaxies, even entire universes. The probability of such fluctuations is unimaginably small, so small that they would not occur even once in a Google of years. But in an infinite future, probability loses its meaning. Everything that can happen will happen, eventually. What would it mean if a star spontaneously appeared in the heat-death universe? Imagine the darkness, unbroken for eons upon eons, and then, suddenly, a flicker of light, a concentration of matter, forming from the quantum void. This star would burn for a few million or billion years, and then die, return to the void, and the darkness would resume. And if life evolved on a planet around this star, if conscious beings looked up at their lonely sun, they would never know that they were an accident, a random fluctuation in an otherwise dead universe. They would live their lives, love their loves, wonder at their world, and then they would vanish, their existence forgotten by a cosmos that has no one left to remember. These are strange thoughts, and perhaps they are wrong. Perhaps our theories are incomplete. Perhaps the heat-death universe has properties we cannot yet imagine. But even if quantum fluctuations do not produce stars and planets, they will still produce something. Particles, fields, brief configurations of energy that flicker into existence and fade away. The universe in its final state is not truly dead. It is simply dreaming, producing phantoms and shadows, echoes of the structure and activity that once filled it. And perhaps, in some sense, that is enough. Let us rest with this thought. The universe dreaming. Even in death, there are dreams. Even in silence, there are whispers. Even in darkness, there are flickers of light. The story of the universe does not end with the heat-death. It simply becomes quieter, subtler, more mysterious. And perhaps that is a fitting conclusion. For a universe that began with a mystery, the Big Bang, to end with another mystery, the quantum whispers of the eternal night. As we journey through these cosmic timescales, these visions of ultimate fate, it is natural to wonder what it all means. What does it mean that the universe will end this way? What does it mean for us, for our lives, for our hopes and dreams and aspirations? Let us take some time to reflect on these questions, not to answer them definitively, but to explore them together. The first thing to recognize is that the heat death is not something to fear. It lies so far in the future, so far beyond any timescale relevant to human existence, that it has no practical impact on our lives. The sun will not burn out for 5 billion years. The last stars will not fade for 100 trillion years. The last black holes will not evaporate for 10 to the power of 100 years. These timescales are so vast that they have no meaning for individual humans, or even for humanity as a species. We will live and die. Civilizations will rise and fall. Entirely new forms of intelligent life may evolve, all long before these cosmic events unfold. So the heat death is not our fate. It is the universe's fate, and the universe is patient enough to accept it. But even so, the knowledge of ultimate ending can affect us. It can shape our perspective on existence, our sense of meaning and purpose. Some people find this knowledge depressing. If everything ends in darkness, if all our achievements will eventually be forgotten, then what is the point? Why strive? Why create? Why love? This is a valid response, but it is not the only response. Others find liberation in this knowledge. If nothing lasts forever, then we are free from the burden of eternity. We can embrace the present moment, appreciate what we have while we have it, without clinging to the illusion of permanence. The cherry blossom is not less beautiful because it falls. The sunset is not less glorious because night follows. The universe is not less meaningful because it will eventually reach equilibrium. There is a philosophy found in many wisdom traditions that teaches the acceptance of impermanence. In Buddhism, this is called anicca, the recognition that all conditioned phenomena are impermanent. This teaching is not meant to produce despair, but liberation. By accepting impermanence, we free ourselves from attachment and find peace in the flow of existence. In Stoicism, the ancient Greek and Roman philosophy, there is the practice of memento mori, remembering that we will die. This practice is meant to focus the mind on what truly matters, to encourage virtue and wisdom, to help us live fully in the present. The heat death of the universe is simply memento mori on the largest possible scale, a reminder that even the cosmos is impermanent. Even the stars will fade, even the black holes will evaporate, and if we can accept this, truly accept it, we may find a deeper peace than we ever imagined possible. There is another perspective worth considering, the perspective of cosmic optimism. Yes, the universe will eventually reach the heat death, but that is not all there is to say. Consider what the universe has accomplished in the time it has had. From the primordial plasma of the Big Bang, the universe has created galaxies, stars, planets. It has created chemistry, biology, consciousness. It has created beings who can look up at the stars and wonder, who can compose symphonies and write poetry, who can love one another across the vastness of space and time. The universe has been, in some sense, a success. It has done remarkable things. It has explored countless possibilities. It has achieved wonders beyond imagination. And when it finally rests in the eternal peace of a heat death, it will have earned that rest. I offer these reflections not as answers, but as invitations. Invitations to think, to feel, to wonder. What does the heat death mean to you? How does it shape your sense of meaning and purpose? How does it affect your relationship with the cosmos? I would love to hear your thoughts in the comments. Let us create a community of cosmic contemplation, a space where we can explore these profound questions together. We are not alone in facing the mystery of existence. We have each other, and that, perhaps, is meaning enough. Before we continue toward our final destination, let us pause to appreciate something remarkable. Right now, at this very moment, the universe is young. It is vibrant, it is alive with light and activity, and we are here to witness it. This is an extraordinary privilege. Let us not take it for granted. When you look up at the night sky, you are seeing light that has traveled for years, centuries, millennia to reach your eyes. The light from the nearest stars has been traveling for about 4 years. The light from the center of our galaxy has been traveling for about 26,000 years. The light from distant galaxies has been traveling for millions or billions of years. In a very real sense, when you look at the night sky, you are looking back in time. You are seeing the universe as it was, not as it is. You are practicing a kind of cosmic archaeology, recovering information from the distant past. And what information you can recover? The patterns of stars that ancient peoples used for navigation, the galaxies whose light carries clues about the evolution of the universe, the cosmic microwave background, that faint afterglow of the Big Bang itself. Every photon that reaches your eye is a messenger from the past, carrying information about events that happened long before you were born, long before humanity existed, perhaps even before the Earth formed. This is one of the miracles of astronomy, that we can see so far back in time, that we can study the history of the cosmos simply by looking up. In the far future, this will no longer be possible. As the universe expands, the light from distant objects will be stretched to longer and longer wavelengths. Eventually, it will be shifted beyond the visible spectrum, beyond the infrared, beyond any wavelength that could be detected. The cosmic microwave background, which today provides crucial information about the early universe, will be diluted and red-shifted into nothingness. Future astronomers, if any exist, will find no evidence that the Big Bang ever occurred. The distant galaxies, which today we can photograph and study, will recede beyond our cosmic horizon, carried away by the expansion of space. Their light will never reach us. They will vanish from our observable universe. In the far future, the night sky will contain only the stars of our own merged galaxy, Milkomeda, and eventually, not even those. The cosmos will lose its memory. The evidence of its own history will be erased by the very expansion that carries it into the future. This is a sobering thought, but it also highlights the importance of the present moment. Right now, we can see the history of the universe written in light. We can study the cosmic microwave background and learn about the first moments after the Big Bang. We can observe distant galaxies and trace the evolution of cosmic structure. We can measure the expansion rate and infer the existence of dark energy. We are living in a special time, a time when the universe is still readable, when its history is still accessible, when the evidence of its past has not yet been erased. This will not last. In the far future, the universe will be as mysterious to any observers who exist as it was to our ancestors who looked up at the unchanging stars and wondered. So let us appreciate what we have. Let us treasure the knowledge we have gathered. Let us remember that we are privileged to live in an era when the cosmos can be understood. And perhaps, if intelligent beings persist far into the future, they will carry this knowledge with them. Perhaps they will preserve records of what we have learned, pass them down through countless generations, keep the memory of the universe alive even as the evidence fades. This is one way that meaning can persist: through memory, through knowledge, through the preservation of understanding across the ages. The universe may forget its own history, but perhaps its children will remember. There is one more possibility we should consider before we complete our journey. What if the heat death is not the end? What if the universe, or something like it, begins again? This is the idea of eternal recurrence, the concept that the cosmos may be cyclical, that endings are followed by new beginnings, that the story of existence repeats forever. The idea of eternal recurrence is ancient. It appears in Hindu cosmology, where the universe goes through endless cycles of creation and destruction, each cycle lasting trillions of years. In Stoic philosophy, the ancient Greeks imagined that the cosmos would collapse in fire and be reborn, identical to what came before. In modern physics, there are several mechanisms that might allow for cosmic rebirth. One possibility involves the quantum vacuum. We have mentioned that the vacuum is not truly empty. It seethes with potential energy. What if this vacuum energy could somehow be released, triggering a new Big Bang? Some physicists have speculated that the vacuum of our universe is not in its lowest energy state. It may be metastable, like a ball balanced on a hill. Eventually, perhaps after an almost infinite time, it could decay to a lower energy state, releasing enormous amounts of energy in the process. This vacuum decay could destroy our universe as we know it, but it might also create something new, a new universe, with new physical laws, new particles, new possibilities. Another possibility involves the nature of space-time itself. Some cosmological models suggest that our universe is just one bubble in an infinite multiverse. New universes are constantly being born through processes we do not yet fully understand. Our universe had a beginning in the Big Bang, but the multiverse may have no beginning and no end. If this is true, then the heat death of our universe is not the end of existence. It is simply the end of our particular cosmic bubble. Other bubbles continue, new bubbles form, and the grand tapestry of existence continues to unfold. Yet another possibility involves the nature of time itself. If the universe is cyclical, then time may be cyclical too. The heat-death may not be followed by infinite stasis, but by a new Big Bang, and a whole story may repeat, perhaps identically, perhaps with variations. If this is true, then in some sense, nothing is ever truly lost. Everything that has happened will happen again. Every person who has lived will live again. Every moment of joy and sorrow will recur, eternally. This is a dizzying thought, but it is also a comforting one. For if the universe is truly cyclical, then the darkness of the heat-death is not permanent. It is merely a pause, a breath between chapters, before the story begins anew. We do not know which of these possibilities, if any, is correct. Our physics is not yet complete. Our understanding of the cosmos has many gaps. But what we can say is that the heat-death, as profound as it is, may not be the final word. There may be more to the story, more that we cannot yet see or understand. And perhaps that is fitting. The universe has always been full of surprises. Why should its ending be any different? We are approaching the end of our journey now, the end of this documentary, though not the end of the cosmic story. Before we speak of the final image, the image of our sun as a black dwarf, let us take a moment to meditate on darkness itself. Darkness has always frightened humans. In darkness, we cannot see. We are vulnerable. We are alone. Our ancestors huddled around fires, pushing back the night. They filled the darkness with stories of monsters and spirits. They longed for the dawn, even today. We light up our cities, banishing the natural dark. We've made ourselves a species of perpetual daylight, rarely experiencing the true darkness that once enveloped the earth each night. But darkness is not inherently evil, or frightening, or bad. Darkness is simply the absence of light. It is neutral, peaceful, restful. Think of the darkness of the womb, where we all began our journey. That darkness was not threatening. It was nurturing, protective. It held us safe as we grew. Think of the darkness of sleep, which we seek each night. That darkness is not frightening. It is restorative, healing. It allows us to rest and dream. Think of the darkness between the stars, which has existed since the universe began. That darkness is not empty. It is full of potential, of possibility, of the raw material from which stars and planets and life emerge. Darkness is not the opposite of creation. It is its complement, the background against which light can shine, the silence that gives meaning to sound, the rest that makes activity possible. The heat, death of the universe is the ultimate darkness, the longest night, the deepest sleep. But it is not a horror. It is not a catastrophe. It is simply the universe resting after an unimaginably long day of activity. The darkness of the heat. Death is peaceful. It is complete. It has no fear, no suffering, no loss. It simply is. And perhaps in that darkness, there is something sacred, something worth contemplating, something worth accepting. As you listen to these words, perhaps in the darkness of your own room, preparing for sleep, I invite you to make peace with darkness. Let go of your fear of the night. Let go of your resistance to endings. Let go of your need for the light to last forever. Embrace the darkness as a friend, a companion, a part of the whole. For in the end, darkness is not the enemy of light. It is its partner, its balance, its completion. And when the universe finally embraces the eternal dark, it will not be dying. It will be coming home. And now, we come to the image that will close our journey. The image I promised you at the beginning. The fate of our own sun. Not the distant heat death of the universe, but something closer, more personal, more intimate. The story of how our star, the star that gave us life, will become a black dwarf and drift forever through the eternal night. Let us trace this path from the sun we know today to the crystal sphere it will become. Right now, our sun is a middle-aged star, about 4.6 billion years old. It has been burning hydrogen in its core for all that time, converting 4 million tons of matter into energy every second, radiating light and heat across the solar system. This light has warmed our planet, powered our biosphere, made life possible. For billions of years, the sun has been the center of our world, the source of all our energy, the god that ancient peoples worshipped. But the sun's hydrogen supply is finite. In about 5 billion years, the hydrogen in its core will be exhausted, and the sun will begin its final transformation. When the core hydrogen runs out, the sun's core will contract, becoming hotter and denser. The outer layers will expand, and the sun will become a red giant, hundreds of times larger than it is today. The red giant sun will engulf Mercury and Venus and perhaps even the Earth. The inner planets will be vaporized, returned to the cosmic dust from which they formed 4.5 billion years ago. But this is not the end. The red giant phase is just a transition, a dramatic but temporary stage in the sun's evolution. After perhaps 1 billion years as a red giant, the sun will shed its outer layers. They will drift away into space, forming a beautiful planetary nebula, a glowing shell of gas illuminated by the hot core within. And at the center of this nebula, the sun's exposed core will remain, a white dwarf. The white dwarf sun will be a strange and wonderful object, about the size of the Earth, but containing roughly half the mass of the original sun. Its density will be unimaginable. A teaspoon of its material would weigh as much as a truck. At first, the white dwarf will glow brilliantly, with a surface temperature of perhaps 100,000 degrees, hotter than the surface of any normal star. It will shine with a fierce white-blue light, illuminating the expanding shell of gas around it. But it will generate no new energy. It will simply be cooling, radiating away the heat stored within it, growing dimmer and redder with each passing eon. Over billions of years, the white dwarf sun will cool. Its surface temperature will drop from 100,000 degrees to 10,000, to 1,000, to 100. Its color will shift from white to yellow to orange to red to deep infrared, visible only to instruments that can detect heat radiation. And eventually, after trillions of years, even the infrared radiation will cease. The white dwarf will have cooled to the temperature of the cosmic background, a few degrees above absolute zero. At this point, it will have become a black dwarf, the final state of stars like our sun. No black dwarf has ever existed. The universe is not yet old enough for any white dwarf to have cooled this far. We predict their existence based on physics, but we have never observed one. Our sun will be among the first generation of black dwarfs, a pioneer of the final state, a herald of the cosmic night to come. And what will this black dwarf be like? It will be utterly dark, emitting no light, no heat, no radiation of any kind. It will be invisible against the background of space, detectable only through its gravitational influence. It will be utterly cold at the same temperature as the void itself, neither absorbing nor emitting energy, in perfect equilibrium with the cosmos. It will be utterly still. No nuclear reactions, no convection, no activity of any kind, just a sphere of degenerate matter, crystalline and pure, frozen in time. And it will drift forever, through the darkness of the dead galaxy, through the silence of the empty universe, through the endless night that follows the death of the last star, a crystal ball the size of the Earth, containing half the mass of the sun, carrying within its frozen heart the memory of light. This is what our sun will become. This is its destiny. This is how the star that gave us life will spend eternity. And so, we come to the end of our journey, but not the end of the story. The black dwarf that was once our sun will drift through the universe, for timescales beyond imagination, beyond comprehension, beyond meaning. Let us imagine its journey. Let us follow it into the forever. The black dwarf drifts through space, dark against dark, cold against cold. It passes through regions where stars once burned, where planets once orbited, where civilizations once flourished. But all of that is gone now, long gone, forgotten by the very atoms that once composed it. The black dwarf does not know it was once a star. It has no memory, no consciousness, no awareness. It simply is a sphere of matter moving through space, obeying the laws of physics. For all eternity, time passes, but time has lost its meaning. 1 trillion years go by, then another trillion, then another. The numbers grow so large that they cease to have any significance. And still the black dwarf drifts. Unchanged, unchanging, a witness to the long silence of the cosmos. Perhaps, once in a great while, something happens. Another dark object passes nearby. Their gravity briefly pulls at each other. They change course slightly, and then continue on their separate ways, into the void, or a stray particle, wandering through the emptiness, strikes the surface of the black dwarf, adding its infinitesimal energy to the mass, and then the silence returns. These events are so rare, so subtle, so insignificant that they barely register against the backdrop of eternity. And still the black dwarf drifts. But even the black dwarf cannot last forever. Remember what we said about proton decay? On timescales of 10 to the power of 40 years or longer, the protons themselves may decay. The matter that composes the black dwarf may slowly dissolve, particle by particle, returning to the radiation from which it came. If this happens, the black dwarf will gradually lose mass. Over spans of time that dwarf even the ages we have discussed. It will shrink, evaporate, fade, and eventually there will be nothing left, nothing but radiation, diffusing through the void, spreading thinner and thinner, approaching but never quite reaching absolute uniformity. This is the final fate of our sun, of all stars, of all matter in the universe. Not destruction, but transformation, a return to the light from which everything emerged, a completion of the cosmic cycle. And now, dear listener, I want you to rest. We have traveled so far together through such vast reaches of time and space. We have witnessed the birth of stars and their death. We have seen galaxies collide and black holes evaporate. We have contemplated the heat death itself, the final state of the universe. These are heavy thoughts, profound thoughts, thoughts that can weigh upon the soul. But I want you to know that you are safe, you are here, you are now, and the vast future we have discussed is so far away that it cannot touch you. Close your eyes if you haven't already. Feel the weight of your body against whatever surface supports you. Feel the gentle rhythm of your breath, in and out, in and out. You are made of stardust. The atoms in your body were forged in the hearts of ancient stars, billions of years ago. Stars that lived and died, long before our sun was born. And one day, those atoms will return to the stars, will be incorporated into new worlds, new forms, new possibilities. The cycle will continue, as it always has, as it always will. The universe may end in darkness, but that darkness is not cold or frightening. It is peaceful, it is complete. It is the universe finally resting after an unimaginably long journey. And you, dear listener, you are part of that universe. You share its nature, its essence, its destiny. When you sleep tonight, you participate in a small way in the great cosmic rest that awaits all things. Your breathing slows, your thoughts quiet, and you drift into the gentle darkness of dreams. So rest now, rest and be at peace. The stars are still shining. The universe is still young. There is still so much time, so much possibility, so much life to live. Tomorrow you will wake and the sun will rise, and you will carry within you the memory of this journey, this meditation on endings, this lullaby of the cosmos. And perhaps you will look at the world a little differently, see the light a little more clearly, appreciate the warmth a little more deeply, for you know now what awaits at the end of time, and you know that it is nothing to fear. If you were the last star in the universe, would you feel lonely or peaceful? Perhaps you would feel both. The loneliness of being the only light in an infinite darkness, and the peace of knowing that your light matters, that you are holding back the night for just a little longer. This is what our sun does every day. It holds back the night. It provides warmth and light. It makes life possible. And one day, it will rest, as all things must rest, but not yet. Not for billions of years. Not for countless tomorrows. So, for now, let us rest together, in the knowledge that we are not alone, that we share this journey with each other, and with the universe itself. Thank you for traveling with me tonight. Thank you for listening. Thank you for being here. If you enjoyed this journey, please subscribe to our channel. Leave a comment sharing your thoughts and feelings, and know that you are always welcome here. Whenever you need rest, whenever you seek peace, whenever you want to contemplate the vastness of existence, I will be here. The stars will be here. The universe will be here, waiting for you in the gentle darkness, where all things find their rest. Good night, dear friend. Sleep well and dream of stars.